Okay, so hi everyone, welcome back. Um, so we're gonna basically just do kind of the same thing we did yesterday. So I have some problems um, that I kind of picked out, and I was thinking that we can work on them, and I'll try to use the breakout rooms thing. Let me see if I can see where to do that. It's a little bit. Oh yeah, okay. I see. Okay, I see how to make them. So I think I'll try to do that. We'll see. Apologies in advance if it gets all messed up. But yeah. So before we get into the questions, or before we get into the problems that I had in mind, if you guys have questions, again, now is a perfectly good time to ask them. And if you could try to use the raise hand feature, I guess, this time, because I know where to look for it now. I don't know if it's like enabled. If you can't see how to do that, feel free to just like talk, I guess. Any questions about the lecture? Let's see. Rahul?
Yeah, just a question about writing proofs. Do we have to cite like O4, O3, or A1
Uh,
like line or
right, yeah. Classic question.
right?
Yeah. So basically it really just depends on the context, but I'll say when it comes to like the axioms, right, like stuff like the O1 through 5 or like A1 through 4, M1 through 4, you basically only have to cite those axioms explicitly for like the problems specifically about proving parts of like theorem 3.2, I guess, right? That's basically the only context in which I'll ask you to actually cite those axioms, because
Like the direct consequences of the axioms. I got
yeah,
you.
exactly. And like as a general rule, right, like the standard of justification in a proof sort of like shifts depending on what you're trying to prove and like depending on the context, I guess. So like it's really hard for me to outline exactly what like needs justification and what doesn't need justification in a totally general sense. But the way I try to describe it usually is like it should be like you should feel like it's almost stupidly obvious that like the assumptions you're using to justify something actually justify that thing. And if it's ever like not super obvious, you should consider trying to like break apart what's actually going on there and then describe it, I guess. Okay. And you should like imagine someone else in your shoes who hasn't solved the problem, um, or like, yeah, who's like a little bit, behind or something on the problem or whatever. Like they should be able to understand exactly what you mean and like what you're thinking when you write like because of A, B, and C, like conclusion D is true or something, right? Um, but like, yeah. So and it also kind of just depends on like how big the proof itself is. Like if the proof is really short, then you don't want to skip over like the main step of the proof, right? Even if it's really obvious. Um, if like skipping over a step cuts out like half of the length of the proof or something, or like more, then you should like consider actually just putting that step in, I guess, right? And it never hurts to be a little bit more detailed than you have to be. So I don't know. Hopefully that helps. I'm sorry that it's like kind of this ill-defined thing, but you just have to like you. I don't know. Yeah, you kind of have to go with your gut, and I hopefully the homework grader will like leave some comments. I'll try to tell them to try to leave some comments about like whether your proofs are well written or need a little bit of polishing or whatever. I don't know how much they'll actually do, but yeah.
Okay, thanks. One more question.
Yeah,
If we're doing our homework in LaTeX, can we
yeah.
just also just like add a picture of the lecture questions? along with the homework. So
Yeah, sure. Yeah, if you want to.
okay.
Other questions? Audrey? Let's see. Do I have to?
Oh, no. Oh,
Oh,
hello.
yeah.
I'm kind of I would appreciate if you went over again your little outline of the proof for the Archimedean property
Oh,
from your
right.
videos today.
Sure.
I was just confused by the very last part where you made a K A and you added 1 and it was
Yeah.
greater than the supreme.
Yeah. So basically, the way that one works is we have here, let me draw like a line. And okay, so we have 0, and then we have like the multiples of A, right? And then there's B over here. We're trying to show that eventually these exceed B, right? So we suppose, we sort of imagine that they actually never make it there, right? So they stop somewhere, like they never get past some place before they get to B, right? So what that says is, so yeah, what that would say is that B is an upper bound on the multiples of A. So right, if no Sorry, I know you were only asking about the very last bit. I just want to make sure everyone gets the context. So if B is an upper bound for all of the multiples of A, then that means, so, you know, there's a supremum of the set of all multiples of A, right? So we're going to say this is the supremum of all these multiples, right? And we call it S naught. So, oops. So we have S naught, that's the supremum here. Now, because it's a supremum, what that means is it's the least upper bound. So any smaller number is not allowed to be an upper bound for all these multiples, right? So if you subtract A, so let's say this is S naught minus A now, right? So we just subtracted A from here. This is not allowed to be an upper bound for the multiples of A, because then it would be a smaller upper bound than the supremum, right? So what that means is that there has to be some multiple, Ka, which is, so K is some natural number such that Ka is greater than S naught minus A, right? That's what this is saying, okay? But then if you just add A to both sides, then we get that K plus 1 A is greater than S naught, right? So that's kind of what I was trying to represent with this. But I didn't really explain this sort of algebraically. So, but intuitively, if you want to think about it, it's just like this like interval here is only a distance A wide, right? So if you add A to something, that has to shift it like out of this interval, because it can't, if it stayed inside, then this interval would have to be like longer than A, right? So yeah, so you end up over here, and that contradicts the idea that S naught is actually an upper bound for all the multiples of A. So yeah, they just have to keep getting bigger, and eventually they have to pass B. That's the Archimedean property. So yeah, this was the Archimedean property.
Okay, thank you.
Yep.
I think that clicked better this time. Thanks.
Yeah, great. Any other questions? Keep them coming. These are good. Yeah, so reasoning about like suprema and stuff is something that you want to practice a lot. Like this whole idea of when you find a supremum, you can exploit the fact that it's supposed to be the least upper bound and say that like any lower number, you have to be able to find elements of the set which are actually bigger than that number, basically, right? That's like the really useful thing about taking a supremum, is that you can like always find numbers that are bigger than any smaller number than that in the set that you're looking at. Happens a lot. Okay, so I don't see any other people with questions for now. So let's go ahead and look at some problems. Actually, the first one, I'll say, the first one will just kind of be a warm-up, okay? So it's not, I won't really do the whole like breakout rooms thing just because the problems will be very quick. I'll give you guys like, 5 minutes to think about them maybe. It's just gonna be some of these like, find the supremum of this set, but you don't have to like justify it really, you just have to think of what it would be. It's good to practice these kinds of things just to be, because you want to get to the point where like, if you look at a set, you can if the set has any like reasonably like non-horrible description, I mean, obviously sets can be just like very complicated. Their description of a set can become like arbitrarily difficult to understand. But for any set that's sort of like readily that you can like visualize, you want to like be able to quickly identify what the supremum probably is, even without like fully manifesting like a proof of that fact in your head, right? Like that's a general principle in math too, is that like you want to be able to quickly sort of like identify things, like identify features of like what you're looking at, and think of things that are like probably true without necessarily knowing how to prove them right away. But then once you think of something that's like probably true, you can start to think about like why it would be true, and then you can formulate a proof of it. So, okay, so let's just say this. So, right. Give the suprema and infima of the following sets if they exist. Okay, so I'll just take some of these kind of at random. So let's try 0, 1, union 2, 3. That's one of them. Union from n equals 1 to infinity of 2n plus 1. The intersection from n equals 1 to infinity of -1 over n, 1 plus 1 over n. Let's do, yeah, n plus -1 to the n over n for n and n. Just a couple more here. Hold on, actually, write them over here. Let's see. Oh yeah, this one. 1 minus 1 over n, 1 plus 1 over n. And let's try this one. X squared. Okay. So, yeah, we'll resume at 5:25.
Quick question.
Oh yeah.
Is the supremum and infima, are they defined only for the real number set? Like, it doesn't make sense to say the suprema of the rational number of rational numbers.
Yeah. So
they can't
suprema and Yeah, so suprema and infima are well-defined concepts for subsets of any ordered field. Really, any ordered set, actually. The ordering is the only thing that's necessary for a supremum or an infimum to make sense. However, whether or not the supremum or infimum exists for a specific set, like, so what you could say is that, like, if you take a subset of the rational numbers, right, the supremum, since the rational numbers are a subset of the real numbers, right, the supremum of that subset of the rational numbers is guaranteed to exist in the real numbers, right? But it might not be a rational number.
Okay.
Yeah. So, but like, there are still plenty of subsets of the rational numbers that have suprema and infima within the rational numbers themselves too, right? I mean, any subset that just has a rational supremum or infimum will do. So you can like define the concepts of suprema and infima for subsets of any ordered set.
Okay.
Yep. Okay. All right. So it should be a pretty quick little exercise here. So this one's like kind of obvious. The supremum is 3. Oh my God. For some reason, threes especially. Oh my God. Threes really give me a hard time on here for some reason. The infimum is 0. Jesus. All right. now let's see. Let's do this one, this second bullet, this union of 2n and 2n plus 1. Actually, so does anyone want to say what they got for this? If you and explain, feel free to like raise your hand. If anyone's brave. All right, no one wants to. That's fine. Maybe we'll get there. It seems like you guys are actually willing to talk, so yeah, maybe we'll have people actually answering problems. But these are pretty easy. So this one, I think it's good to practice like trying to visualize what these sets look like on the line. So in this case, it's just like all of the like intervals between like even numbers on the left and then odd numbers on the right. So you start with like 2 and then you have like 3. Oh my God. Right, you get an interval there and then you get like an interval between like 4 and 5. And it kind of like alternates like that, right? So, and then you get like 6 and 7. So it should be fairly clear from the picture that 2 is the infimum and it's unbounded above, so the supremum sort of doesn't exist. Although actually I kind of forgot that I was drawing this from a part of the textbook before they defined the whole convention with infinity and minus infinity. So I'll say the sup equals infinity, right? If you wrote does not exist, that's perfectly fine too. This is literally just code for like both of those are just code for like the set is unbounded above, because obviously any bounded above set must have a supremum by the completeness property. So, and then the infimum is 2. So, okay. How about this one, this intersection? This is it gets a little bit trickier. I mean, like, especially if you don't have a lot of experience with intersections and stuff like that. Anyone? Oh yeah, okay. Rahul?
I got the infimum to be 0 and the supremum to be 1.
Yeah, very good. Do you want to sort of explain why?
Because as it's the intersection, so I guess the most common intersection of all the sets is when n becomes infinity, and
Okay.
the lower bound is going to be 0.
Mm-hmm.
Once it hits infinity, the upper bound is going to be 1.
Yeah, you're looking at like the limits of these expressions basically as n approaches infinity. Yeah, that's a very common way of thinking about things like this. I would say in this case it works. Thank you, by the way. That was good. I would say it works perfectly well in this case, but I would actually caution you guys against thinking like that too much, just because sometimes, like in this case, it's sort of helped by the fact that like all of these sets, every time n increases, the next set just gets smaller, but it's still inside of the previous one. So basically at any stage, like as you increase n, if you keep taking the intersection over and over again, all you're left with is just like the last set you had, right? But like if things, like if there was randomly a set early on that was like, just displaced away or something like that in a weird position, then you'd end up like artificially having like a different endpoint, I guess. So what I'll say is actually, so here's one way of thinking about this that makes it kind of pretty easy. This entire set literally just equals 0, 1. Okay. I mean, as a set, these two things are equal to each other. But here's how you should think about y, okay? So when you take an intersection, all you're doing is asking what are the points that are in common among all of these different sets. So we have a bunch of different intervals. We have an interval that's like -1 to 2. We have an interval that's like -1/2 to 3/2, right? -1/3 to 4/3, and so on. We have all these intervals, and we have to ask which points are actually in all of those intervals at the same time. And basically, you can just kind of go through all the different real numbers, and ask in each case, like, is this in every single interval or not? And if it's in every interval, you can put it in the final set, right? So like when I think about a negative number and I ask, okay, is a negative number, are there any negative numbers in this intersection? The answer is no, because eventually, right? Like if I take up negative 1/7 or something, right? Negative 1/7 is actually a member of the first like 7 of these intervals, right? Once n equals 7, you get negative 1/7 to like 8/7 or whatever. Negative 1/7 is in all of those sets. But then as soon as n gets bigger than 7, so once n is like 8 or bigger, this interval becomes too small and negative 1/7 is no longer inside. So that's why it's not in the overall intersection, right? And the same thing goes for numbers that are like bigger than 1, right? Any number that's bigger than 1, eventually this number will get smaller than that. So it will be excluded from the intersection in the end. So that's why there are no numbers below 0 or above 1 in the final set. And then all the numbers between 0 and 1 are pretty clearly just in all of these intervals. So that's why those are in the final set, right? So then once you kind of get a handle on like what the set actually is, you can just look at this and be like, oh yeah, the supremum is, or the infimum is 0 and the supremum is 1. So I think it's actually a really good idea to get in the habit of just thinking about like asking yourself the question, is a given number in all of these intervals or not? Like, what does it take for a number to be inside every single one of these intervals? That's the sort of very careful way of thinking about these things. Now let's see. So this one, n plus negative 1 to the n over n. What did you guys get? Anyone want to volunteer? Okay, so this one, let's see. You just kind of, so if you think about like what these numbers do as n increases, right? Like it's pretty clear that overall, these numbers tend to get bigger and bigger and bigger, right? Because this term over here just gets smaller and smaller. So actually just from that alone, you can kind of tell that this should be unbounded above. So the supremum should be infinity here. Now the question of the infimum is just, you kind of just have to look at the first few values and find the smallest one, because eventually it'll get so like big enough that it'll never go back down, you know, because there's this kind of alternating term that like could cause it to decrease going from one term to the next, but eventually that becomes irrelevant. So like if you start at n equals 1, you get 1 plus negative 1, so that's 0. So just write down the first few terms of the sequence. So you get 0, and then you get 2 plus 1/2, so 3/2, and then you get 3 minus 1/3, which is, you know, well, clearly bigger than 0. So I guess that's like, you know, 8/9. I'm very bad at arithmetic. Yeah, so anyway, so, but clearly like it's not ever going to go back down below 0 after this point. So 0 is the end. Okay, any questions about any of these so far? Okay, how about this intersection here? Anyone want to volunteer a guess as to like what the set actually is? What numbers are in this set? Yeah, Shanak. Sorry if I pronounced that
Is it just
wrong.
1?
Yeah, this is literally just the set 1. Very good. And it's like if you think about it the same way that we did over here, you'll see like basically, yeah, any number smaller than 1, this lower bound will eventually like get bigger than that, and any number bigger than 1, this upper like endpoint will get smaller. So all of those numbers get thrown out eventually, and then 1 is just left in all of these. So that's the only number. So 1 is the supremum and the infimum of this one. Okay, and then this set here is just literally just this half interval, right? Any positive number or 0, those can all be achieved as the square of some real number, right? So the supremum is infinity, the infimum is 0. Okay, very good. So let's, any questions just about this entire thing?
For the second to last question, it ends up
Yeah.
being I guess it ends up being open the open interval 1 comma 1, right? Technically,
Right.
but
Okay.
does
So
that technically mean 1?
no, right. So this set by convention we would consider empty. So that's
Okay.
actually, this is a good example of why it's like not always perfectly valid to just take the limits inside of the
Okay. Yeah.
expression here. Yeah. Very, actually extremely good question. Thank you. Like I want to illustrate like how you have to think, there's a very specific way you have to think about expressions like this, like set theoretic expressions. The only like truly correct way to think about these is literally just to ask yourself like which numbers are in all of these things and which ones aren't. Like there's no
Okay.
better way of doing it basically. Yeah. Mm-hmm. Any other questions? Okay. So let's actually I'm just going to clear this here all. Let's do another problem here. So how about this one? Hold on. Yeah, here we go. So this is 4.12 in the book. So let I be the set of real numbers which are not rational. So these are the irrational numbers. Right. Show that if A is less than B, where A and B are just real numbers, any real numbers, then there exists some x in I such that A is less than x less than B. So remember there was this denseness property for the rational numbers. And so it turns out that the irrational numbers have the same property. So in between any two real numbers, you can always find an irrational number. And there's a hint for this, which is to show that the set of numbers of this form, where R is a rational number, is a subset of the irrational numbers. Okay, so for this one, I'm going to give you guys like maybe 10 minutes to discuss. I hope that's not too short. And I'm going to try to do this breakout room thing. So let's try this. Breakout rooms. Da, da, da. I see. Okay. Let's try 3 rooms. Yeah. So how do I? Oh, here we go. Yeah, let's do that. So great. Okay. You guys seem to be joining them. So yeah, let's say we'll resume at 5:50. All right, yeah. So I didn't realize that it takes a minute. I don't even have like an option to like, but I guess it makes sense because it'd be kind of awkward to just like instantly destroy the breakout rooms. So yeah, we have about 10 seconds left. Let's see. Okay, so I think, yeah, everyone should be back now. Okay, great. So would anyone like to explain just the hint, like how to get to this point? How do you show that this set here is a subset of the irrational numbers? Any volunteers?
Hello?
Yeah, Alexei?
Yeah, you can show that the sum of a rational and irrational number is irrational.
Yeah, basically. How does that work?
Well, a rational number is two integers divided by each other.
Mm-hmm.
And so then if you add an irrational number, then you won't get an integer, you'll get an irrational number on the
Okay. Yeah.
numerator.
Yeah, that's definitely like the right intuition. A bit of a more rigorous way to phrase the argument would be to say, like, suppose R is rational and R plus square root of 2 equals Q is another rational number, right?
Yeah.
Then the square root of 2 would be Q minus R, which also has to be a rational number because it's the difference of two rational numbers, and that's a contradiction. So this is just a simple contradiction argument that shows that any number of this form, the sum of, and this actually works like, yeah, like you were saying, for any, this could be any, so, or any element of the irrational numbers. So that's very good. Thank you. So does anyone want to explain why this hint actually helps us get to where we're trying to go here? Okay, well, I can just I can explain it. Also, by the way, I should kind of apologize. I kind of forgot momentarily when I picked this problem. I kind of forgot that like I wanted these problems to resemble the ones on the homework, and like this one is a little bit like not the most sort of relevant thing for the homework. I mean, it's a good exercise, I think, but it might have been better to do something more with like Suprema and Infima and stuff. So, you know, sorry about that. In the future, I'll try harder to like keep it really, really like germane to the homeworks and stuff. But anyway, so let's actually finish off this this argument here. So what we have is basically, if you think about it like visually in your head, what you can imagine is that like what we found is a subset of the irrational numbers that just looks exactly like a shifted version of the rational numbers, right? Obviously, that's not all of the irrational numbers, but we found a subset in here that's just like this like shifted version of the rational numbers. So basically, since the rational numbers kind of cover everything, they kind of cover the whole real line, then this new subset should also cover it, right? So what we can do is say like, let A and B, you know, let A be less than B, then A minus the square root of 2 is less than B minus the square root of 2. So we kind of shift it all back. And then since Q is dense, there exists an R in Q, obviously, such that A minus the square root of 2 is less than R less than B minus the square root of 2. So then by shifting it all back over, by adding square root of 2 to everything, you get A less than R plus square root of 2 less than B. So this, and so what we showed before from the hint is that this is in the irrational numbers. So we just furnished an irrational number in between A and B, which is what we were trying to do in the first place. So that does it for that little proof there. But yeah, like I said, in the future, we'll definitely be doing more like proofs with suprema and infima, and then convergence. So I finished recording lecture 3, which is about convergence and limits of sequences. So that'll be up pretty soon. And I'll see you guys tomorrow. So thank you.
Oh, hi, Professor. I actually have a question.
Oh yeah, sure.
Yeah, so like I wonder for explaining the hint, you said we can use proof by contradiction, but when we're in a breakout room, we're thinking, can we use a rational zero theorem to say that like the whole thing is irrational, the set?
Right, to say that r plus square root of 2 is
Yeah.
irrational using the rational zeros theorem. You could possibly do that. Let me think for a second. Yeah, you can find a, you probably can do that actually. Because like r plus square root of 2, like, wait, r plus square root of 2, you know, if you call that, like, let's call that b or something.
Yes.
Then like b minus r squared minus 2 is 0. And so, but the difficult thing would be to say that, yeah, so because then what you'll end up is with, yeah, so it'll take a lot of work, I think, to do it, because what you'll end up with is, so you have like b squared minus 2rb plus r squared plus 2 is 0. So this is your constant term basically, right? Yeah. And you have no idea what r is. So what you're basically trying to argue is that like, well, first of all, the coefficients here are not integers. So you'd have to like you'd have to write r equals like m over n, and then like clear the denominator, right? So you'll end up with something like, the constant term will become like, oh, okay, interesting. Yeah, it becomes like m squared plus 2n squared, right? Yeah. Is the constant term. And then also like the highest degree term will end up with a coefficient of n squared. So you'll basically say that the rational roots will be like factors of this number over factors of n squared. And then you have to like argue that none of those are actually roots or something like that. So it gets like a little bit
complicated.
There are actually theories that can let you like proceed with the proof that way if you want, but you basically have to be learning like an entire other branch of math. So
yeah. Okay. Thank you.
Interesting idea. Yeah, cool idea. Yeah. Any other questions?
Are we doing oh, sorry.
Go ahead.
Okay, thanks. Are we doing Dedekind cuts in this class?
Yeah, no, skipping it this time, man. Okay. Last time I taught this, I tried to do that and it was like horrible, dude. Like everyone freaked out, and like it was because they're not, the problem is like for this class, I have to say like the return on investment is like pretty low. Like they're hard to understand for most people, and all you get out of it is just like some kind of philosophical confidence that the real numbers actually exist. But like you don't end up using them for anything else later on. So I like them. I think they're cool. You know, I wish that we could do it, but there's just not enough time and it's too difficult. So yeah. Okay. But I encourage you to read about it if you're interested. Any other questions? One other person had a question, I think.
Yeah, I'm just wondering, how do we find the supremum and infimum of the null set?
Oh yeah, so like, okay, this is a interesting question. They're kind of just defined to be a specific thing. So the supremum of the null set should actually be negative infinity, and the infimum of the null set should actually be positive infinity. And it's hard to understand. So this is the only set, at least I'm pretty sure this is true. This won't actually like really matter for us. You shouldn't really be encountering situations where this matters, I guess. Usually, like if there's a case that you're concerned about where a set you're looking at might be empty, you can just handle that case separately in a totally different way without having to like know what are considered the supremum and infimum. But yeah, this would be the only set where the supremum is less than the infimum. And so the justification behind this is actually pretty interesting for anyone who's interested in like foundations of math or anything like that. There's some kind of like cool logic going on here, but basically like to say that the supremum is negative, you know, if you were to say that the supremum equals something, right? What you're saying is that, or yeah, actually think about it this way. Think about the set of upper bounds on the empty set, right? Basically, every single number is an upper bound on the empty set because there are no elements of the empty set which are bigger than that number, right? If you take a random number and you ask like, is this an upper bound on the empty set? The answer is always yes, because you can't find a number in the empty set which is bigger than the number you picked, right? So the set of upper bounds for the empty set is just all of R, right? And similarly, the set of lower bounds, I'll just say LB, is also all of R. So now the supremum is supposed to be the least upper bound, right? So it's just the like minimum of this set here, right? Which is negative infinity. Similarly, the infimum is supposed to be the greatest lower bound. So it's positive infinity. Kind of neat.
Right, that makes sense.
Yeah. It's like super weird when you first see this. It's like, how is this possible? But yeah, I think this kind of makes it a little bit more intuitive. Any other questions? Okay, very cool. Thank you for the questions. Those were really good. I'll see you guys tomorrow.
Thank you so much.
Mm-hmm.